Welcome to this explainer. Every single time you ask your voice assistant a question or just search the web, you're actually forcing a machine to crack the incredibly ambiguous code of human language. So how do they actually pull that off? It's a fascinating journey. Today, we're diving into the mathematical wizardry behind sequence labeling, which is essentially the master key to unlocking machine understanding. Think about it. We've taught computers to perform ridiculously complex tasks, like calculating massive equations or routing global internet traffic in literally milliseconds. But reading and actually understanding human language? That remains one of the absolute trickiest mysteries out there. Why? Because language is beautifully messy. And to a machine, our rich, nuanced communication just looks like flat, lifeless strings of text. Even Shakespeare knew that words carry their own unique, context-dependent tune. As he famously wrote in A Midsummer Night's Dream, to each word a warbling note. And it turns out capturing that exact warbling dynamic is exactly what modern natural language processing is trying to do. It's a massive challenge that linguists have been obsessing over since the ancient Greeks, like Dionysius Thrax, and it really forms the entire foundation of modern machine learning. Now, the core mystery for machines here is ambiguity. Let's take a simple word like back. It can act as an adjective, like in a backseat, or totally flip and be a verb, like back the bill. It can even act as a noun or an adverb. It has a complete identity crisis that depends entirely on the words surrounding it. If a machine just looks up the word back in a dictionary, it's going to get real confused real fast. And this exact same problem applies to semantic meaning, too. Take the word Washington. Does it mean a sports team going up 2 games? A government passing a seatbelt law, or just a guy crossing the Delaware River? This presents a massive disambiguation headache for any AI trying to extract actual, reliable facts from a normal sentence. To see how machines solve this case, here is our roadmap. We are going to look at 1. The ambiguity of language, 2. Decoding parts of speech, 3. Identifying named entities, 4. Hidden Markov models, and 5. Conditional random fields. Let's jump right in. Section 1. The ambiguity of language. Let's start by looking at just how massive this ambiguity problem actually is in our everyday speech and text. What's totally fascinating is the data from real-world text. While about 85% of words in a standard dictionary only have one grammatical meaning, the words we actually use the most are the biggest troublemakers. In running text, over 55% of the words we type and speak are ambiguous. That means more than half the time, a machine has to guess which version of a word we actually mean.
Section 2. Decoding parts of speech. So how do we start fixing this? Well, our first major linguistic clue to solving this massive ambiguity is assigning parts of speech, which you'll often hear called POS tags.
Human languages are generally divided into 2 main categories. First, we have open classes. These are your nouns, verbs, and adjectives, the ones that constantly evolve with fun new slang like iPhone or to ghost. Then we have closed classes. These are the fixed grammatical function words, things like prepositions, determiners, and conjunctions. Knowing whether an unknown word is a noun or a verb instantly tells a machine so much about the likely neighboring words, making it an absolutely crucial first step in parsing any sentence. Let's build on this using a really simple sentence. Janet will back the bill. We're going to use this as a mini narrative throughout this explainer just to see exactly how a machine sequentially labels and makes sense of each and every word. Is back a noun here, or is it a verb? Let's see how the machine actually figures it out. Section 3. Identifying named entities. Beyond just basic grammar, we also need to extract the semantic meaning of proper nouns, which brings us to named entity recognition, or NER for short. The real challenge here is that entities like names, locations, and companies very often span across multiple words. To solve this tricky segmentation problem, machines use a brilliant little setup called the BIO tagging system, which stands for begin, inside, outside. So the word Jane marks the beginning of a person entity. Villanueva is inside that person entity. The word of is outside any entity, and United begins a new organization entity. It's a super clever way to turn complex span recognition into a really simple, word-by-word sequence labeling task. And astoundingly, using these sequence structures, modern statistical models can actually hit a 97% accuracy ceiling in part-of-speech tagging. That effectively matches human performance. Just let that sink in for a second. Machines are practically as good as human experts at identifying the grammatical roles of words in a text. Crazy, right? Section 4. Hidden Markov models. So how exactly do they reach that 97% accuracy? Enter the classic predictive tool, the hidden Markov model. At its core, an HMM is this brilliant probabilistic framework. The machine observes words, those are the visible events on the page, but it must mathematically infer the hidden sequence of grammatical tags driving them. It relies heavily on the Markov assumption, which basically says that when you're predicting the next tag in a sequence, the distant past doesn't matter, only the present tag matters. The model makes its decisions based on two core probabilities derived from massive sets of training data. First up, transition probabilities. This asks, how likely is one tag to follow another? For example, a modal verb is highly likely, like 80% likely, to be followed by a base verb. Second, emission probabilities. How likely is a tag to produce a specific actual word? For instance, if the tag is a modal, there's a 31% chance the actual word emitted is will. By multiplying these probabilities across a sentence, the machine scores all the different possibilities. But calculating every single combination for a long sentence, that would take an absolute eternity. So to navigate this, the HMM uses something called the Viterbi algorithm. It sets up a probability grid, recursively calculates the most likely previous step by step, and then traces back the best overall path. Think of it exactly like finding the fastest route on a GPS map, by only remembering the most efficient paths to each specific intersection. Let's bring this all back to Janet. The Viterbi algorithm calculates the highest probability path for our sentence. Janet will back the bill. Because will is a modal, the transition probability heavily favors a base verb coming next, so the algorithm confidently and correctly tags back as a verb rather than a noun or an adverb. Mystery solved. Section 5. Conditional random fields. Because as brilliant as hidden Markov models are, they do have one major blind spot. That blind spot? Unknown words. You see, HMMs are generative models, meaning they only look one step back to make a decision. That's a bit rigid, and if they haven't seen a word before in their training, they basically fail. This is where conditional random fields, or CRFs, step in to save the day. They are discriminative models. They can look at a global set of diverse features all at once to discriminate among possible tag sequences. They don't just look at the last tag, they can look at the word itself, the word after it, its spelling, literally anything. This means a CRF can hunt for rich, custom clues. It can check for capitalization and abstract word shape. It can look for suffixes like ed to guess it's a past tense verb. It can even cross-reference a massive geographical database to figure out if an unknown capitalized word is a city or a person. This makes CRFs incredibly powerful for sequence labeling tasks, especially since new, unknown words are constantly entering our language. These foundational models, HMMs and CRFs, taught machines the absolute basics of cracking our deeply ambiguous linguistic code, successfully reaching that incredible 97% human accuracy ceiling. But understanding how these statistical models essentially match human performance using just transition probabilities and handcrafted features leaves us with a pretty wild final thought. What happens when we unleash the massive context-heavy power of modern neural transformers on this problem next? Thanks for joining me on this explainer, and keep questioning how the systems around you really work.